Hi and welcome to the sixth episode of our MiniStealth tutorial series where we're using SpriteKit and GameplayKit to create a simple roguelike stealth-like game. And today we're going to be working on enemy AI. We'll use a state machine to allow our enemy to patrol and pursue our player when the player is seen and try and catch a player. So let's get started. So first a bit about state machines. State machines are really a staple of software development. They're used in many different situations and are particularly well suited to model behavior that can somehow be described as a state, something that something is in, and then how you go from one state to the other. So an example could be a traffic light that has three states, yellow, orange and green, and red, yellow and green, and then you could have the transitions modeled that you can go from green to yellow and yellow to red, but red always goes directly back to green. And this way of modeling is really suited well for describing enemy and non-player character AIs, because you could describe what an enemy is sort of doing and how it changes the behavior by changes in the environment. But it's not just limited to enemies or NPCs. We'll see another example in a future episode. So our enemy's AI is going to be pretty simple. The state machine will only have two states, patrolling and pursuing. So if the enemy hasn't seen the player yet, it starts off patrolling, that's walking around the level, and once it sees the player, it changes into the pursuing state and then tries and catch the player. We'll reuse the visibility component to determine whether we can see the player. And once we're in the pursuing state, we never go back, so we keep trying to catch the player no matter what. And we'll do that by having a bit of naive pathfinding, so that's how it tries and move towards the player. It's a really naive implementation because it can easily get stuck behind something. We'll implement more complex pathfinding in a future episode. For now this will be enough, and we'll wrap the state machine into a new component, the simple patrol component that we can add to enemies. So to create the state machine itself, we're going to use a feature in GameplayKit called GKStateMachine and GKState. These two classes, or these two abstract classes, help us define state machines. There are two things I want to note before we dive in. The implementation of a state machine in GameplayKit is really flexible and highly scalable, so it's coded in such a way that it's applicable to many different cases. And the obvious advantage is flexibility. The downside is it tends to be overkill for really simple stuff like our game. So there is a lot more code than needed to only implement the two states that we have in this game. And in that way, you could argue that a simpler approach would be better. On the other hand, I think it's nice to demonstrate how GameplayKits State Machines work. And we will see a more simple example of a state machine in the future episode, so you get to see both approaches. And the second risk is that GameplayKit is an Objective-C based API, so it doesn't interacting with it doesn't really feel very Swifty. There'll be a lot of subclassing. You'll use the any type. There will be a lot of reflection, and to make things worse, if you look at the developer documentation, there's constant links to the programming with GameplayKit guide that would explain how to use it. However, all the code examples in that guide are Objective-C based, which makes them pretty difficult to use unless you're already very well vested in Objective-C. So that's a bit of a risk, but it won't stop us for today. So to create the state machine in GameplayKit itself, we need to subclass GKState, and we'll also add world updatable and owned state conformers. World updatable is protocol we saw before that allows us to update, call an update function and pass the world. And owned state is a new protocol we'll add to allow the state to know which entity owns it. And we need that information to, for instance, move the owner of the state and the state machine around. So we'll create two subclasses, a patrolling state and a pursuing state. And in each of these classes we'll implement an isValidNextState function that returns whether, when it's trying to transition into a new state, whether that's a valid transition. So this way you can, for instance, make sure that if you are in the pursuing state, you can never go back. Then there is the state machine itself. That's an instance of a class GKStateMachine that initializes with the two states. And that has, for us, two important functions. It has an enter function that tries and transition to a different state, and it has an update function that it gets from world updatable that allows us to call the update of the current state, and that way we can see whether we can perform the behavior that's expected of the state, as well as try and transition to different states if needed. So our implementation sequence will be, we'll first set up the basics for the state machine we're going to use. So there's a bit of boilerplate code there. Then we'll create the patrolling state and the pursuing state, and create the simple patrol component. Then we can see whether the state actually works. Then we will add the patrolling and the pathfinding behavior, and finally we will color the field of vision of the enemy so you can see how far it sees. That makes the game feel a bit more fair, because it becomes more predictable whether the enemy can see you or not. So let's start with the first. Let's set up the basics for the state machine we're going to use. And for that we go to Xcode. And I first want to go into our model and create a new group called State Machines. And we will start by opening it and creating the own state protocol. And we will import GameplayKits, and we'll create a protocol called own state that applies to GK states, and it only has one requirement. We want to have an owner of type MSEntity, and it should at least be readable. So we don't require it to be writable here. And this should be a get. And that's one. Then what we also need is to add a protocol conformance to the GK state machine, and we'll do that by writing an extension. World updatable. So we'll import GameplayKit, and we'll create an extension to GKStateMachine where we're adding conformance to world updatable, and we'll provide a default implementation. We'll first see whether the current state is a world updatable state, so we'll use optional unwrapping and have a new variable called current world updatable state equals the current state as world updatable. And if this fails, we'll send an error stating that you should only use GKState subclasses that conform to world updatable in this game. And we'll pass back the, we'll call then the update in world function for our world updatable state, because we determined here that it conforms to that protocol. So that's nice. So I think that is the basics done, and we can now start creating the states themselves. And we do that in a subfile, in a new file in the subfolder called patrolling state. And this one too requires GameplayKits. We'll create a final class patrolling state. It'll inherit from GKState. It's world updatable and conforms to own state. This means it needs an owner. And we also need a target, so we need to determine what it's trying to find when patrolling. So there's we initialize using an owner and a target. And finally we call the super method, and then we need to implement the isValidNextState function. And this way works by determining whether the passed in state is of the type pursuing state.type. Pursuing state we haven't defined yet, but this is the way these work. And finally we need to implement an update function, and for now we'll just print patrolling state update. This error will go away when we create the next state, so we'll create a new state called pursuing state, and this is very similar. So this too imports GameplayKit. This has a final class pursuing state that inherits from GKState, conforms to world updatable and own state. So we need an owner, and this one too needs a target, and this one needs a member-wise initializer as well. And we need to call the superclass initializer, and here too we need to implement the isValidNextState function, and this one will always return false because we never go back to the other state. So once we're pursuing the target, we're never letting go. And finally we need to also implement this update function. We'll implement the actual behavior later. Now this one should no longer complain. And we now have our states. So what we can now do is create the AI simple patrol component and add it to the enemy. So we're going to use them. So we're creating a new file in components called AI simple patrol component. And this because we are going to do most of the coding in the states themselves, we really don't need a lot of code in this one. We need to import GameplayKit, and we'll create a final class AI simple patrol component. That's our type GK component and will conform to world updatable. And it will have a state machine to hold its states. We'll initialize it later, so we'll just say state the type here. We also need an initializer, and that requires the owner and the target, not for the state machine itself, but for the different states it can have. It needs that. We create a state machine as a GKStateMachine with the following states, with the patrolling state, and that one needs the owner and the target, and the second state is the pursuing state, and that too needs an owner and the target. Then we need to go to the default state. So we're saying to which class we should transition. And finally we call super.init. This class has a requirement to implement another initializer, and we need to implement the update function, and this one is really simple. We have a state machine, and that has now an update in function because it conforms to world updatable. And this is all there is to this component right now. So it's just running this state machine. Now let's add it to the enemy. So we have our enemies here. Let's add a component. Well, first let's add a visibility component and give it a range of 7 or so it can see around. And then add the AI simple patrol component, and the owner will be the enemy and the target will be the player. And I think this should now work. Well, at least it should show that it's calling an update function in one of the states. So let's give it a go. So our player's here. Put it a bit over to the side and I'll show this one. So when we walk around, there's a lot of other stuff being shown. Let's quickly get rid of that. I think it's this one. Let's restart. So let's walk around and we can see we're calling the update function in the patrolling state. Nothing is happening yet, it's not working yet, but that's what we need to implement next. So we'll add the patrolling and then pathfinding behavior. To do so, first I will create a small helper variable to the visibility to quickly see if a tile is visible without having to use switch cases each and every time. So we'll just say switch on self, and we'll have a case visible. Then we'll say return true, and otherwise we'll return false. So this way we can very quickly inspect whether a visibility at least is visible, regardless of the amount of light it receives. So let's go to our patrolling state first, and let's go to our update function, get rid of the print, and first see can we spot the target. So let's get our visibility component. If visibility component tile visibility, and we'll look at the target position, is visible. This is an optional so it will default to false. Then we'll say our state machine, enter pursuing state self and return. So this is where it transitions state. If we can't see the player, we'll simply patrol, and we'll do that by moving our player in a specific direction. We will define a sort of forward direction, and we'll do so by adding a heading to our entities. So that's basically the way to look. So let's add a heading. But heading is something we haven't defined yet, so let's create a new file called heading. And this will be an enum. And we'll give it a raw type of integer, and it will be case iterable. I'll explain why we have a raw value and case iterable later. First, let's define the cases. So we have north, northeast, east, southeast, west, and northwest. Which ones am I missing? East, southeast, oh, should have south, southwest, west, and northwest. So there should be 8 right now. And then we'll create a new variable called 2Vector, so we can transform the heading into an actual direction. So we'll switch on ourselves. I'll say we have a case for north, and we return vector 0.1, and we have northeast, that's 1.1. And also we want to transform the other way around, so we want to go from a vector that's passed in to a heading. And this is where the case iterable protocol comes in. This gives us an all cases array, and then we can use inspect it and try and find where the 2Vector value is the same as the one that's passed in, and returns nil if it can't find any. So now our MS entity should have a heading, and we should be able to initialize it, for instance, going north, and this should be a variable because we want to be able to change heading. So let's go back to our patrolling state. So we want to move in the direction we're looking at. So what we'll do is we'll go if owner.try move into the heading as a vector in our world.map. If for some reason this fails, for instance you try and walk into a wall, we'll just rotate 90 degrees. And this is the reason why we had the raw type of integer for the enum, because now we can do some mathematics to find a new heading. So we'll try a new heading raw value equals to the owner.heading.raw value, and we can add 2 to that. So basically what we're then doing is say we're here, we can go to there, 2 down. But of course at some point in time this value will become too large and won't be a valid case anymore. What we'll do is we'll simply take the modulus and use that to wrap around at the end of the array back to the start, and then we can say our owner.heading equals our heading, a raw value of our new heading raw value. If for some reason this doesn't work, we'll just keep the heading we had. So this is the patrol behavior. Now let's look at the pursuing behavior. Pursuing will be a little different. We won't be checking how we can go to a different state. We'll just try and find which direction we need to move to walk to the player, and we'll do so by defining first two variables, a direction x and direction y. And we'll just say if our target position.x is larger than our owner position.x, so the target is above the enemy, then we'll set the x to 1. If on the other hand it's smaller, then we'll set it to -1, and something similar for the y-axis if target.position.y is larger than owner.position.y. It's above, so we'll say it to +1, and otherwise we'll set the y to -1 if the enemy is above the target. And then our direction will be a vector of dx and dy, and then we'll try and use this to create a new heading. So we'll take a heading, vector to heading for direction. If this works, then we'll set the owner.heading to the new heading. And once we've rotated, we'll try and move the player in the owner, so the enemy, in that direction. So we'll try move direction in the world top map. And because this one is not looking at whether this is really successful or not, even if it gets stuck in a wall, it will just keep trying to go in that direction. So that's why this is a very naive way of pathfinding, and this won't be a very smart enemy. But it should be enough for now, and I think this one will be able to now chase the player around. So let's have a look. So it's walking, and oh, we already got caught. It's trying to chase us, and it caught us. If you want to see the enemy a bit better, what we can do is we can go to the game scene, and instead of the player we can look at entities. And I know number 2 is an enemy, and use that to determine what we can see. So if we walk around, we can see it's patrolling, and if we move up, at some point in time it will see us and try to find us. So let's put this back to player. This is working. So finally, I want to color the field of vision for the enemy, so it's a bit more easier to determine what the enemy can see and what it can't see. And to do so, I want to color the tiles that the player can see as well as the enemy can see. So we need some form of overlapping tiles. And what we'll do is we'll go into our game scene, and we'll first create a new function called overlapping tiles. That it takes a dictionary of vectors and visibility 1 and the second one. So this will allow us to compare two visibility, tile visibility variables. So we have a vector visibility 2, and what we want to get out of this is a new vector visibility dictionary that contains the ones that are overlapping. So we'll first look at only the visible tiles for the ones that were passed in first. So we'll do tiles that filter, and we'll only filter out the ones that are visible. So this is again where we use our isVisible helper function, and we do the same for the other ones that are passed in. Then we're going to use sets because they make it very easy to overlap or find an intersection between sets. So we have a coordinate set of type vector from visible tiles.keys, and we'll have a second one for visible tiles 2, and then we'll have an intersection that is going to be a coord set 1 dot intersection coord set 2, and we'll have a result. It's going to be a vector to visibility dictionary, and we're going for each coordinate in the intersection, we'll say a result coordinate equals to tiles 1 coordinate. So the visibility of that one, and then we'll return the result. This last part should be possible using a map function as well, or a reduce function as well, but a bit more complicated. So let's keep it at this. So we created we determined which tiles are visible for both a player as well as an entity. And what we want to do is we want to color those differently. So we shown here our entities. We shown here our tiles. So after we've drawn all the tiles, what we'll do is we'll have our other visibility components to our world entities. And we'll filter out the ones that we don't want to have the player. So we'll say whether that one is not the world.player. And we'll filter out the ones that don't have a visibility component. So we'll say take a compact map. We'll get an entity in and we'll try and find a component of type visibility component. And now we should have a list of visibility components other than the player. And then we'll go over each one. We'll say let our overlapping tiles be equal to the overlapping tiles. That's a function. And we'll use the tile visibility from the visibility component for the player as well as the other visibility component. And then for the tile in overlapping tiles, we'll find a map cell. And we'll switch on the tile.value, so on the visibility. If it's not visited, so there's no overlap, then we won't do anything. If it's visited, we won't either, only if it is visible. Then we want to color it and have the light value, so then we'll use the console put background of mapcell.name, add correct position, and we'll use a different color. And we'll use a hue of 0.1, saturation of 1, brightness of lit, and an alpha of 1. So these should now have a different color. And this should be visible. I think we should now be able to see the field of vision of the enemy as well. So let's give it a go. So we have our player. When we move around, we can see the orange ones are the visibility of the enemy. It's a bit difficult to see, but it really is there. And it's awesome, it's following us around. So that's enough for this episode. It's been a big one. Next one, we're going to improve our AI by adding pathfinding using GameplayKit features, and that way our enemy will also be able to follow us even if there's some obstruction in between. So thanks for watching and have a good day.